Okay, so in this video, we are going to consider extending our language that we have worked with in the previous videos and also material from the CSE 505, the required semantics in our language that would enable us to have the machinery necessary to reason with, specifically now that we have added to imp assert and panic, we want to be able to reason about them and we want to define them in our small step semantic. So we also added the steps. Here, notice we have added a step assertion true, a step assertion false, and we have added our panic. And if you really talk about what we talked in class and what the usage of panic really is, programmers are not really going to write the word panic in their own program. Really, the way this program is designed, we can really put assert anywhere in the program right now. We cannot really put panic anywhere. Panic is really an internal part of our system, which is a small part of the operational semantics. And it acts as a signal that an assertion has failed in the past. And notice, we don't have a Hoare rule to talk about panic because programmers are not going to talk about panic either. So consequently, we don't have to ever prove a program that contains panic is correct. And really, if they wanted to have the equivalent of panic in their program, they can just write false instead. And then as a last note, this rule here just allows us to propagate panic out of a sequence. Okay, let's talk about Hoare logic and Hoare triples. And if you're following this material with the slides, remember, anytime there is a horizontal line on the slides, that gets converted to an inductive proposition. And if you look at week 6 slides from the course, we have 7 rules for Hoare triples, and we are going to convert those 7 rules down here to have constructors for them. Now, remember, Hoare triples take 3 things as inputs: an assertion in the beginning, an assertion at the end, and a program that executes between those 2 assertions. And they're true if the assertions hold before and after the execution. And just to familiarize ourselves with the definition of an assertion, let's have a look. It's defined up here. And it's all one line. It's just a function from valuations to props. So it takes in a memory and then comes up with a claim proposition about that memory. So the Hoare triple definition is going to allow us to reason about these 3 things. So evaluation, a function that evaluates something from a memory to a prop, a program, and then another function that evaluates a memory and gives us a prop. So let's begin. And for sake of brevity, we are only going to talk about the constructors here that are of more importance to us. If we have evaluation V and the predicate V holds, then we have evaluation that is non-zero when we evaluate on our V. So here what it's saying is if we want to prove P after an assertion, we not only have to show or prove P before the assertion, we also have to prove that we will not evaluate to 0. And then this version that's commented out here is a version that more closely matches the slides. So here below the line, we just have the same pre and post conditions. And then above the line, we have an obligation, which is not a Hoare triple. It's an implication that in all valuations V, if P is true, then E is non-zero. Let's move on to an example. And remember this driving example we had from before is a 2-counter program. So takes some input, sets y to be that input, initializes x as 0, and then loops while y is not 0, increments x, decrements y, and then once y is 0, just terminates. And the thing we were interested in proving was that at the end of the program, x was equal to input. And remember, we had a similar proof in a previous video. And what we want to show here is how Hoare logic is going to make this proof way easier than what we had to deal with before. So now we are going to use our proof system to prove the following. So in any evaluation where true is true, or any valuation state, if we execute the two counters program, which is this program up here, then you will end up in a state where this equation holds. So our goal is exactly this theorem that we are going to prove. So this is our goal here. And to make our job easier, we are going to unfold the AST of the program, in other words, the function. Now, looking at the new goal, we have a Hoare triple, which has this precondition here, and also this post condition. Neither of these two have changed from before, and this program or AST in the middle. And following from our previous videos, now if you want to see which rule we can apply, we can look at what rules are even applicable in our program, and then proceed with that. So when we look at the root node of the syntax tree of our program, there are a few rules that we can find from Hoare logic that are applicable. The good thing here is that the Hoare logic proof system is also syntax driven. So by looking at the root AST node, we can easily figure out which of the 7 rules in our Hoare logic system we can use here. And the small caveat here is that if the rule that we are trying to apply doesn't work, we probably have to use the wiggle room rule to make things work. So the root AST node in this program is the sequence operator. But if that's not immediately visible to you, there's a trick. We can make COQ displayed in notations. And that makes it pretty obvious that the root AST node is sequence. So we go ahead and apply the sequence rule here, which spits out 2 sub-goals for us to work on. And let's take a moment and ask ourselves, why did the sequence rule give us 2 sub-goals? And the answer is that that's definitionally the way the sequence rule works. If you want to show that you have a Hoare triple with precondition P and postcondition Q, and a sequence C1, C2, which is basically your program, then you have to show that you can step from the assertion P through the first part of your sequence to an intermediate assertion R. And then from that intermediate assertion, by executing C2, you're able to step into Q. So it shouldn't be surprising that we are getting 2 sub-goals here. The first goal is about the assignment statements that happen before the loop, which itself is a sequence of 2 different things. So we go ahead and apply the sequence rule again. And now we have 3 sub-goals, which is 1 for each assignment statement in our program, and then 1 for the rest of the program, which is the file. Now, since Hoare triples are syntax directed, we look at the root of this node and apply the corresponding rule. But unfortunately, that is not going to work here. If you were to apply the assign rule here, what would happen? So it's not going to work because the assign rule expects the precondition to be some kind of the substitution of the post condition. So since this fails, we have to resort to the wiggle room rule. Now, remember, when we are using the wiggle room rule, if you're doing some sort of a proof on a surface like a whiteboard or a piece of paper, precondition, program followed by a post condition, usually we focus on one side of our proof. And then let's assume, like the slides from the class, this P implied an A. And then given that A, we had a situation like this, where after running the program, we ended up in a B, but then if B, we had implied Q, then we can use the wiggle room rule, and that usually applies on one side or the other side of our program, but not both. So the course staff has actually created the equivalent of that in COQ on these lines that you can go look at. And again, in a situation like this, we can just set B to be equal to Q. And if we do that, then we can apply the wiggle room to the left, where we have maybe changed A to be P. And that would just get us all the way with our proof. And that would just allow us to make progress towards the goal of our proof. And then notice these are derived rules that we are allowed to use in reasoning. But in order to use these, we don't have to add anything new as far as definitions go to our proof system, because they follow from the other things we have previously added to our proof system. And then this consequence rule is actually the official name of the wiggle room rule. And in particular, this consequence left, what it does is that it's the wiggle room rule, but it doesn't change the post condition. It keeps the post condition the same. And it uses things we had in our machinery from before. So we don't really need to add this to our proof system because it's a special case of other rules. So going back to our proof, our precondition is currently not in the right shape. So we're going to apply this consequence left to change the shape of our precondition, which gives us two additional subgoals. One of them says, well, it's not immediately known what you want to change the precondition to. But if you were going to tell me what the precondition was going to change to, you'll have to show that that implies true. And then you'll also have to prove that true implies that. But now we are stuck because we don't know what question, we don't know what question mark P prime is. So we need to make some more progress and then come back to this. So we are going to put this on the shelf for now, which is a syntax we have not seen before. So here we are using this particular syntax with shelf to delay this proof until the very end. So now that we replace the precondition with a placeholder, the assignment rule that used to fail because we were in the wrong shape previously, now to see what that does, actually, let's comment this part out for a second and not shelve this. So question mark P prime is now distinct here, which is question mark R0 substituted with X, which goes to eval 0. And that was the goal of applying the assignment rule to do a substitution in the post condition. So even though this is going to happen behind the scene after we apply the consequence or the wiggle room on the left, because we want to gain some information and then come back to this situation, you're not going to see how this is happening when we shelve it, but that's happening in the background as we are progressing through the other subgoals of the proof. So now we have another subgoal that we are working towards, and there's another assignment here, which means we have to use the assignment rule one more, but it's not a problem that the assignment is not matching, because our precondition here is an empty placeholder. So we can put just about anything in there that we would like to. So in this case, the assignment rule is going to work. And at this point, we have just executed the first few lines, the first 2 lines in the definition, in the code. So let's continue. So now we notice that in this subgoal, the root AST node is a while loop. So we have 2 options. One is to use the wiggle room rule, or we can use the while loop rule. If we try to use the while loop rule here, because for one, our post condition right now is in the wrong shape for the while loop rule. The other thing is that, but then what we have here is also not our looping variant. We need the thing that's you're going to write here for the rule to be our looping variant. Instead, we have this assertion that x is equal to the input. But from the slides and other videos, we know that the looping variant for our loop and this program is x plus y equals to the input, which is our invariant. So we need to negotiate with the proof system and tell it about an invariant by changing the post condition. And here we're going to use the other consequence rule or the wiggle room rule, but this time on the right, to tell the proof system about our post condition. And similarly here, we are going to shelve the precondition until later. And that brings us to the most important line in this proof, arguably the most interesting line in this proof as well, which is this line that applies the while rule. And just a gotcha or something to remember is that every time we apply this rule, we have to apply it with this with syntax to pass in the loop variants that we have in mind. And here, our loop invariant says x plus y always evaluates to input, which is exactly the same loop invariant we've been using for this program in our other examples as well. So that brings us to another proof obligation, which is something about the body of the loop. So we made while go away. And the syntax in the middle of our program is just the body of the loop. And we can poke into this and figure this out, but I'm just going to tell you that the root AST node of this line is the sequence operator. So we can just apply this sequence rule down here. Now the root AST node is this assignment statement. And the precondition is not in a shape that we can easily apply a rule to. So the assignment won't work if you want to make progress on it. So once more, we are going to use the left consequence rule and then shelve what we are getting out of that. So now the assignment rule will work. And then we're in this situation where we have this precondition. So again, because the precondition is a placeholder, we can use the assignment rule again, and that leaves us with no unshelved goals. So now we are going to unshelve using this unshelve command, whatever we had shelved. And that leaves us with 3 goals that all start with assert implies. Let's go ahead and look at the definition of assert implies, and it's up here. And what it does is that it takes 2 assertions, which we defined up here. And it says that for all evaluations, for all memories, the first assertion implies the second assertion. So these goals are a little bit convoluted and hard to read. So let's take a moment to read the very first one. So the hypothesis here says that whatever we are going to show here has to work regardless of our hypothesis, because our hypothesis is always true. Okay, so that actually makes our job harder. So we better be able to prove this part. So we take a step through our proof, and then we intros a bunch of things. And that takes our hypothesis basically above the line. And then what we're being told here is that if we evaluate x plus y in this memory, it should be equal being here, to input. It's the same as evaluating input in the same memory. And this is very convoluted, very hard to read, but notice x is 0 here, and y is whatever input evaluates to in our memory. And so since 0 plus input evaluates to input, we can just simple through this and then auto, that will take care of this goal for us. Okay, so since the rest of these 3 subgoals have similar proofs, and we are looking to run the same tactics for all the subgoals, so we can use this all followed by colon syntax. It's a little bit like using semicolons at the end of a tactic, but sometimes you don't have a way to do that unless you back up and rewrite part of your proof. But what if we structurally weren't able to do something like that? Well, it's very difficult because we'll have to go 20, 30 lines up and do that, and that may change a bunch of other things for us. So here we have 3 subgoals that we commented out. We can say all colon here, and then run these tactics for all the remaining subgoals. And since they are all similar proofs, we can just run this line in our proof, and that finishes our proof.